So today I want to do procedural train generation with a twist. So I wanted to actually add in Catan and then see if we can get the values from Catan. So doing image tracking on Catan, getting that information out, and then doing image processing with the kind of values that you get from that. So that's what we're going to be working on today. So with these more sizable projects, it's oftentimes good to split them up into smaller projects. So we're just going to do a hard split between the image tracking and the train generation. And so from the image tracking, what we want to get from that is going to be the coordinates of all of the tiles. And then we want to be able to send that information into our train generation. So that's going to be the link, and then we can kind of separate those two. So for the image tracking, we basically just cut out a box of the images and then use that for our tracking file. But one of the things that does come up with these types of files is that there isn't a lot of difference between some of these images. So I had to actually exclude a few of the images because they just weren't tracking well enough. One of the things that's neat with Catan tiles is that they are actually all completely unique. They might look similar, but there are small differences between them all. So you can actually get more files working. There is a limit to 20 with the method that we're using. There is also another limit where it requires 25% of the screen to be filled with the image, and that limitation is a lot lower if the image is if it's very easy to find the image. So if you have something that is more optimized for image finding, then you don't have to go so close up to all of the images. So in a lot of these, I have to kind of pan around and grab all the images slowly. So if you had something that was more optimized for image recognition, you could stay a little bit further out and grab those images, but that is a limitation of image tracking within AR Core. There is also this weird kind of anti-synergy between image tracking and the tracking that AR does in general. So general AR does image tracking to kind of tell if the scene is moving or not. An AR scene likes having more semi-distant shots. It doesn't like close-up shots, whereas image tracking kind of requires close-up shots, and you can't really do it at a distance. So there is kind of this weird happy medium thing going on there, but anyways. The image tracking is also done in black and white, so it's actually pretty impressive that some of this image tracking works, because some of these images don't actually have a lot of information in them. Like if you consider the desert one and then you take away the color, it's like a few squiggly lines, and that's all it can track really. And it's impressive that it manages to do such a good job of it. So that's just something that's interesting to think about. So this is a little bit of an aside. So while I was looking for a way of creating a gradient map, I kind of ran into some useful information that will be useful if you're trying to do any extra kind of things with board games and AR and kind of trying to do that augmented aspect. And this has to do with using Delanauy Traingulation to find out nearest neighbors in a tiling situation. In particular, this is really good for hexagonal shapes. But basically what you can end up doing is if you have all your points and you throw it into Delanauy Triangulation, that'll actually get you the edges of all of the nearest points to a point, and you have to do a little bit of cleaning because there's going to be some longer lines, but in general it's a really nice way of getting a really simple graphical map from image tracking, so you can kind of just have the images set up. It's just a really nice way of doing that augmented reality step. So if you'll notice, this is actually a mirrored image, so you actually have to flip this over to get the right image, but that's not such a big deal, and we'll just deal with that more when we're actually getting further along. I think now is a good time to switch over to terrain generation, because we have a good starting point here. There's a few other things that I want to add in, like I want to add in a water outline as well, so but those are some things that we will add in later. For now, I think it's a good time to move on to the terrain generation. So for the terrain generation, there's two main sources that I ended up using a lot of. So Simon Dev has a tutorial series on it, and so does Sebastian Legu. And so Sebastian's is more related to Unity, but it has some really interesting topics when it comes to the differences between biomes, so flipping between biomes. And then Simon Dev's is more JavaScript related, which is what we're going to be using. And both of them are really good tutorial series, so it was just good to have two sources. There's also a lot of other video series on terrain generation. It's something that's very heavily covered, so I think it's good to start with a source and then not try and do everything from scratch. This is my first time doing terrain generation, so if I make any big mistakes, whoops. Anyways, the terrain required quite a bit of messing around with noise parameters, so that was a few hours. So here's some montage extra information about that. But yeah, basically once we got that all working, it was time to combine the two projects together. And so basically you just need to, instead of adding just the names, you need to save those into an array and then use that array as the terrain generation array. So it's fairly straightforward to actually mesh the two projects together. So one of the really important parameters that comes up is the Gaussian mixing value, and that basically is how much you're mixing the tiles together. And if that's a very high number, then you end up over mixing, so you'll end up with these really blended scenes. And if you lower that number a lot, you'll end up with these really harsh cutoffs between the different grain types, so it won't be kind of melded together as well. There are other ways of blending biomes together, but you have to really consider whether you want the scene to be very representative of Catan or whether you want it to be more artistically oriented. And so if you did any other type of blending, it would start making it look less visibly like Catan's. And voila, we have it. So you can actually see from above that it is pretty easy to tell roughly what the Catan looks like. If you change the Gaussian parameter again, like it would be a lot clearer what the tiles were, but then you'd end up with like, it wouldn't look as nice and stuff. So we also had to add in some water. And so how we did that is we basically made the base grid water, and then the tiles are kind of added on top of that. So if there is no tile, then that should be implied to be water. And then we added in an alpha map to kind of make it into a circle instead of the boring square that happens all the time. So if you could just like ignore that I spelled prairie wrong, that would be great. And we can move the tiles around and then it updates in the appropriate way. So we have that working out too, where it doesn't keep points from the last time around. That's always a nice thing to have. Sometimes it works the first time and then the second time it doesn't work. So it's good that we have that sorted out too. For a first go at procedural terrain, I'm pretty happy with this. There is like, you can definitely spend hours more improving it, and like there's a lot of other methods that you can add in where the tutorial series have a bunch of extra topics that we didn't even go into. Like texturing is a big topic on its own that we kind of just ignored, and yeah, I think there's a lot of extras that you could add to this. You could add like a beach outline. There's so many things that would make this look nicer. Adding extra assets on top. So right now the things like sheep, it's just the sheep color of a field if there's no actual sheep there. So if you just added in some small little pixels, that would probably help. Adding in like those extra little details would probably add a huge amount to this, but we just don't have time to do everything. So on to the code. The code for this one is a little bit more extensive than some of the previous ones, so we're just going to kind of go over it in chunks. And so to start off with, we're going to look at the loading part of the code. So you have to get the name of all the files, and then we have to create some of the objects that we are going to be filling up later with some of the information. And then we're going to be creating some of the loading functions. One of the things that does become an issue is that the images take a little bit of time to load. So we need some sort of mechanism for waiting for them and then updating them as bitmaps. And so this is some of the code that we've put together for that, where we kind of increment and we add those things in at each step. And once they are all loaded in, we will be able to use bitmaps, which means that if we start this before the bitmaps are loaded, we'll get an error. You have to do some sort of catching for that. I haven't actually yet, but this ensures that the bitmaps are created after the image is loaded. Once we do that, we can go to the image tracking loop, and we'll change a few things around so that the names update their position and orientation based on the tracking information. And if it's the first time this object is tracked, we will add all of the textures and the meshes to the scene. So the first time around, we'll add them to the scene. And then if it is in a tracked state, we will also update the information for the train generation. For the train generation, there's a bunch of values that we have to initialize as well. And so a lot of these are some of the parameters that we found earlier through trial and error. And then we kind of split the train generation up into 3 chunks. So the first chunk is going to be converting the points that we've gotten from the image tracking into weight map. And how we're going to do that is through Gaussian mixing. So we will basically change the value based on the distance between our point and all of the points in the scene. So this isn't exactly a scalable solution, but it works pretty well for small numbers. So for each point, the further away something is, there'll be a Gaussian drop off for that. So if you are close to a point, it'll be very likely that you'll get a larger value for that particular value. And so we have all these values. We're going to just create an image for each point so that we have all these different weight maps, which are basically how much that point affected the image. So it'll be basically a set of how many tracked images you have of images, and those images will all basically be points. And then what we have to do is we have to convert our image set of weights into an image set of parameters that we use for noise generation. And so how we go about doing that is we get those weight maps and we multiply, we normalize it so that all the weight maps add up to 1 for each value. And then we use that normalized weights to multiply by the parameter set. And so this will basically create drop-offs between each of the points, so that at the center of the point, you should have exactly the parameters, or mostly exactly the parameters of that biome. And then as you kind of move away from the center, you'll start mixing in with those other biomes. And so in the in-between points, you'll end up with a mix of all of the numbers together, and it'll be kind of like a mixed noise situation. And so once we have these parameter arrays, so now we have like a set of images that are each of the parameters, we will use that set to create noise values. And the noise values are basically just going to spit out a height. So now we've gone from all these this huge number of weights to a smaller number to just basically a black and white image of the height. So this will just be a kind of single number associated to each pixel value. And so we have this kind of height map, and then we can layer on top of that a texture map. And the texture map is basically using the weight map, but instead of multiplying it by parameters, we are multiplying it by the color of that particular biome. And then we can add in some extra with the color map and the map together. We can also multiply those together to get a bit of texture to our color. So that'll add in a little bit of noise back into the color map. And then we're just going to kind of create some weight peaks. So we'll change a few different of the values so that the mountains look a little bit nicer and fool around with a few of those details. And yeah, that's kind of the core idea of it. There's some things that we did with the alpha map and making the water, and also we did some stuff with the ocean being the base value. And that's basically all of it. Thanks and have a good day.